Hey everyone, welcome back, and today let's solve Leetcode problem 2044 titled Count Number of Maximum Bitwise OR Subsets. So we're given an integer array nums, and we need to find the maximum possible bitwise OR of a subset of nums and return the number of different non-empty subsets with the maximum bitwise OR value. So an array A is a subset of an array B if A can be obtained from B by deleting some, possibly 0, elements of B. And two subsets are considered different if the indices of the elements chosen are different. So the bitwise OR of an array A is equal to A at 0 or A at 1 or ... up until A at A.length minus 1 because it's 0 indexed. So in example 1, we have the input array nums to be 3, 1, and we'd output 2. Why do we output 2? That's because the maximum possible bitwise OR of any subset in this input array is going to be 3. And since there are two subsets with a bitwise OR of 3, 3 and 3 and 1, we'd output 2, the number of subsets that have that maximum possible bitwise OR value. Right? And note that an input array is considered to be a subset of itself, right? So 3, 1 would be considered a subset of 3, 1. So in example 2, we have the input array nums to be 2, 2, 2, and we'd output 7 because since all of the non-empty subsets of 2, 2, 2 have a bitwise OR maximum of 2, there are a total of 2 cubed minus 1 total subsets, which would give us a value of 7. I won't get into the math of why that actually is, just see that we have 7 total subsets that actually have that bitwise OR value of the maximum OR value of any subset, which is going to be 2. And finally, in the third test case, we have the input array nums to be 3, 2, 1, 5, and we'd output 6 because the maximum possible bitwise OR of any subset in this input array nums is 7, and there are 6 subsets with the bitwise OR of 7, 3, 5, 3, 1, 5, 3, 2, 5, 3, 2, 1, 5, 2, 5, and 2, 1, 5, and so we'd output 6 total subsets as our final output. So with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Sorry about that, guys. I just realized that I was talking a little bit too fast, and I'll try to slow down my speed for the rest of the video for the explanation and coding part. Okay, so kind of for the key concepts and the key patterns to really look for in this problem, the bitwise OR basically combines bits from two numbers, and if either bit is a 1, the result for that bit is going to be 1. And for the subset generation for this problem, basically for every element, we can either include it in a subset or exclude it. And this kind of shapes the structure of a classic backtracking problem. So for our global variables, we're going to have a max OR, which ultimately stores the maximum OR from all possible elements combined, and we'll have a count to track how many subsets actually have the same OR value as max OR. So the way this algorithm is going to be structured, we're going to basically calculate the max OR, which is going to be the OR of all elements together to get the maximum OR possible, and we'll backtrack to actually explore all the different subsets, where at each step, either we can choose whether to include it or exclude it to the current element, right? And if the OR of a subset actually does match the maximum OR of the input, we can increment or increase the count variable, which is ultimately the output that we want to return as the result of our program, right? So with that out of the way, let's just go ahead and dive straight into the code, okay? So I'm going to initialize again, like I talked about before, my max OR and my count both to be 0, right? Again, where max OR stores the maximum OR value we can actually achieve from all the elements of nums. And count is going to keep track of how many subsets actually achieve this maximum OR in our input array nums for every test case. So once I actually do that, now I can regularly iterate over my input array nums to actually update and build up that maximum OR to get the maximum OR value. So I'm going to say for num in nums, I want to set max OR to be the bitwise OR, and it's going to be like this, of num, right? And the key thing here is that the absolute value equal to is the bitwise OR operator, which updates max OR by combining it with each element, right? Okay? And once I do that, now I can actually define my backtracking function, once I've built up my max OR, to actually be the or update the maximum or value of all the different elements of our input array nums. It looks like I misspelled this. There should be backtrack, and there should be a D here. I don't know why I forgot that D. And for my parameters, I'm going to have two parameters, the first one being a current index, and the second one being a current or value. Okay, so pretty self-explanatorily, this basically defines a nested backtracking function. We're going to call it backtrack, where the index keeps track of the current element in nums, and the current or holds the current or value of the current subset built so far in this iteration of this function call. Okay, and like we do for most base cases, we're going to have for most recursive functions rather, we're going to have our base case. But before we have our base case, we actually want to access our count variable. Okay, I could have just defined this count variable in this function. There was a variety of different ways I could have attacked this problem. In this case, I'm going to use the non-local keyword in Python. It's a good introduction of how that works. So it's basically non-local, and I'm going to make a count to be non-local in this nested function, where again, we're using non-local to access and modify the count variable that was declared outside this nested function, but we can still use it in this nested function. That's the really use case of non-local, and feel free to kind of Google that and explore what that really does more in depth outside of this video if you guys don't understand what that really does, right? So once I do that, now I can actually have my base case for this recursive function, like I always do for most backtracking problems. In this case, my base case is quite simple. If the index is actually equal to the length of the numbers, that means we've basically processed all the elements, and if that's the case for any iteration of this recursive function, we can check if the current or of the current subset we've built so far in this iteration, if that's actually equal to the maximum or, great, we know we've found one more subset that actually fits our criteria, and we can increment our count by 1. And ultimately, once we actually complete that base case, we want to return, because we don't want to overcount and we want to completely execute or stop the execution of this function and move on to another function call to meet any other subsets that haven't met this criteria yet, if possible, right? So again, if they actually match the current or value with the maximum or value of a current subset, we can actually increment the count and stop further recursion for this subset using that return keyword in Python, right? And ultimately, until we actually hit this base case, we can recursively call backtrack. And for our parameters, we're going to be how we talked about before. We're going to have index plus 1 and the current or operated or bitwise OR. Sorry, it should be like this, by the nums at that index, right? And we'll recursively call backtrack again for our second case, where we pass in again index plus 1. But in this case, we don't actually change our current or, because we're choosing to exclude it. So to better explain what these two lines of code does, again, we're recursively calling this backtracking function, where on line 12, we have our first option where we can include the current element from that index in the subset. And we'll OR with the current OR value and move on to the next index as our first parameter, index plus 1. And our second option is going to be when we actually choose to exclude the current element from the subset. So we leave the current OR unchanged, but we still move on to the next index and choose to include it or exclude it for the next iteration, right? Okay, and once we do that, we're basically done with the recursion of this backtracking function, and we can exit this definition of the backtracking function, and we can actually call it outside on line 14. And for our parameters, of course, index is going to be at 0 because this is in 0 index array. And of course, our current OR is going to be 0 because we haven't actually scanned through the input array nums yet, and we actually haven't found a subset with a current OR greater than 0 just yet. Okay, once we actually call that, now we can return the count. So to better explain what these lines of code do, again on line 14, we'll initiate that backtracking function or calling from the 0th index, starting with an OR value of 0. And this is going to explore recursively all the possible subsets and choose whether to include or exclude each element in every subset of the input array nums. And ultimately, we can return the count after we call this backtracking function, because it ultimately would have stored the number of subsets with an OR value equal to the max OR value, which would be the base case from lines 8 to 10 in our backtracking function, right? So as you can see, if I were to submit this, unless I made any syntax errors here, this shouldn't be accepted. And as you can see, this is just about as efficient as you can get. So to better explain what the code does overall, we're basically computing the maximum OR possible with all the elements in the list and storing that in the max OR variable. And then we're using backtracking to actually explore every single subset of the list. We'll then count how many subsets actually have an OR value equal to the max OR value, our base case in our backtracking function, and ultimately return the count as the final result. And the reason why is because that would have eventually stored the number of subsets with that maximum OR value. Okay? So for the time complexity of this code, this is going to be big O of n plus 2 to the n. Why is that? We know that the backtracking explores 2 to the n subsets because that's how subsets are defined to be, where n is the length of the num's input array. And the reason why is because for each element we have two choices. Either we can include it or exclude it in our current subset, right? So we have two choices for every element in our input array nums, and so it's going to be 2 times 2 times 2 times 2 up until n, or 2 to the power of n, for the total number of possible subsets we can actually form for this backtracking problem, right? And of course, calculating this max OR is going to also take big O of n time, because this is a one-pass operation where we actually loop through the every single element in the input array nums, and we actually have to update or build our maximum or value accordingly. And so that's why the total time complexity is going to be big O of n plus 2 to the n. And for the space complexity, we know that the recursion depth can actually go up to big O of n, and so the space complexity is going to be linear time, right? So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.